Good afternoon, ladies and gentlemen. My name is Chien-Wei from National Chun-I University in Taiwan. This is the title of my presentation. This is the outline of today's presentation, including 5 parts. First, the introduction will shortly introduce the using of magnetometers and the working principle of resonant magnetometers. Magnetometers can be used in many different areas, like current measurement or other medical application. With a wide expansion of the consuming electric products, micromagnetometers is attended. The micromagnetometers, combining with accelerometers and gyroscopes, can establish local positioning systems. And there are many ways to detect the magnetic field. And in previous research, the resonant type shows the potential that can monolithically integrate with other MEMS device. And this is the working principle of the resonant magnetometers. And here is a release MEMS structure and assessing an AC excitation current, which is frequencies at the natural frequency of the device. And when there is a magnetic field, the Lorentz force, which is modulated by AC excitation currents applies on the device. And its magnitude is related with the effective length and the magnitude of the current. And the device starts to vibrate, and the vibrating motion can be, for the capacitance type, the vibrating motion can be transferred into the electric signal by a capacitance transducers. And next part is the paper survey and the motivation. Among the development of the resonant magnetometers, there can be separated by 2 parts, the sensing axis and the sensitivity. In sensing axis, in this paper, we can it shows the chain of the sensing axis is to sense more multi-axis in one unit. And in this paper, and in the 3rd paper, shows the way that can sense 2 different magnetic field in 1 unit, and locating 2 magnetometers in orthogonal direction that can achieve the 3-axis magnetic field sensing. And this study will based on this sensing mechanism to develop the sensitivity part. And the sensitivity part in in the papers that I mentioned above, there are many ways to deal with the sensitivity, like decreasing the spring constant, increasing the effective length, or shrinking the sensing gap. But there are some issues to do these things. Therefore, this study will propose a new architecture to design the resonant magnetometer for increasing sensitivity. And this study proposed using dual mass vibrating system, which that can enlarge the dynamic displacement of the device to increase the sensitivity of the magnetometers. And the next part is the design concept and the simulations. As a comparison, resonant magnetometers with single mass vibrating systems design is introduced, and its natural frequency is close to the dual mass vibrating systems. And this is a dual mass vibrating system design. And the red part is the second mass, and the blue part is the first mass. And they connect with each other by 4 springs called second springs. And the first mass is connected with anchor by 440 springs called first springs. And the comb electrode is placed on second mass for sensing the in-plane motion, and the handle layer, and the handle layer is used as a parallel plate electrode for sensing the out-of-plane motion. And an AC excitation current is assessed into the structure through the anchor and the springs. When there is an in-plane magnetic field, the Lorentz force, which is induced by current and magnetic field, will make device vibrate in out-of-plane directions. On the other hand, when there is an out-of-plane magnetic field, the device will vibrate in plane directions. And putting two magnetometers in orthogonal directions, the three-axis magnetic field sensing can be achieved. And the model can be simplified as this figure. And the blue part is the first mass, and the red part is the second mass. And the Lorentz force acts on the first mass. And the equation of motion can be written like this, and through this simplified diagram. X1 represents the displacement of the first mass, and X2 is the displacement of the second mass. And the transfer function of the Lorentz force and the dynamic displacement of the second mass can be found, and defining its value as m of s. And next part is the motional current part, and the capacitance type resonant magnetometers is like a resonator with electromagnetic driving and electrostatic sensing, and its motional current can be written like this equation. And the B represent the magnetic field, and through this equation shows that, and we not only can adjust the geometric parameter, but also can enlarge the resonant frequency or the m of s by changing the proportion of the mass and springs constant to optimize the sensitivity. This slide shows the simulation result of the device, and the resonant frequency of the in-plane motion is 4.9 kilohertz, and the out-of-plane motion is 9.6 kilohertz. Assuming device operating at vacuum, which is quality factor is 1000, comparing the frequency response of the single mass vibrating system with dual mass vibrating systems. The red line is the dual mass, and the blue line is the single mass. The simulation shows that the dual mass have 11 dB larger than the single mass vibrating systems. And the next part is the fabrication and the fabrication result and measurement result. And this is the overview of my device, and there are some via hole to connect the backside electrode. And for the fabrication process, the LPCVD nitride is grown on the SOI wafers, and patterning the top side, defining the top side pattern, and then the backside pattern is defined. And second, etching the backside geometry. And before the topside deep silicon etching, the barrier oxide must be removed to prevent the footing effect. And the topside silicon can be etched by deep IE, removing the remained nitride. Then the device can be released by etcher. After wire bonding, the device can be measured. This is the fabrication result of the single mass vibrating systems. Here's the release hole, and here is the sensing cone electrode. And here shows the fabrication result of the dual mass vibrating systems. And also here is the release hole, and here is the sensing cone. And looking down at the bottom of the sensing cone, there's no sign of the footing effect. And here shows the measurement setup of the in-plane magnetic field. The device is put into the Helmholtz coil with horizontal directions, and the Helmholtz coil provide an uniform magnetic field, and which is calibrated by Gauss meters. And there is a transimpedance and provide to enlarge the motional current, and spectrum analyzer can read the electric signal. This is the measurement setup of our plane magnetic field. It's quite similar to the in-plane magnetic field. The difference between them is the directions of the device. In out-of-plane magnetic field, the device is put into the Helmholtz coil with vertical directions. Okay, here's this slide shows the sensitivity, which is measured at atmosphere and with 2 milliamps AC excitation currents. And the red triangle is the dual mass, and the blue square is the single mass. And in the measurement result shows that the sensitivity has the improvement the sensitivity of the dual mass has improvement comparing with the single mass. And the crosstalk of the in-plane crosstalk is 2%, and out-of-plane crosstalk is 4.8%. This slide shows the device measure with the AC magnetic field, and the resolution is shown below. And finally, I will give some conclusions of this study. And for showing the advantage of the resonant magnetometers that can monolithically integrate with other MEMS device, the SOI-based fabrication process, which is used to manufacture accelerometers, is chosen. And 2-axis magnetic field with dual mass and single mass design is realized. And and in measurement result, it shows that the sensitivity has been improved. Be improved. And I would like to thank the following association for fabrication supporting during my research, and thank you for your attention.